In this video, what I'd like to do is walk you through a set of 5 steps that should help you solve virtually any projectile motion question. We'll begin with this relatively simple example, and then we'll move on to a more challenging example later on. Now, step 1 in any projectile motion question is to first draw a picture. Now, in this particular question, a picture has already been drawn. We had a stone that was projected at a cliff of height lowercase h with an initial speed of 42 meters per second directed at an angle of 60 degrees above the horizontal, and the stone strikes at point A 5.5 seconds after launching. And again, if the question had not drawn a picture, you'd want to draw some sort of a picture to help you visualize the problem. So step 1 should be relatively straightforward. In step 2, we're going to superimpose an x, y coordinate system onto the picture. So we've gone ahead and have superimposed an XY coordinate system onto this picture. It is typically the case, though it isn't required, that we place the origin at the point from which the projectile is launched. So in this case, it's a relatively straightforward example. The projectile is launched at ground level, and so our origin is also going to be located at ground level. You recall from algebra that the origin has the coordinates 0, 0. And that will take us to step 3. And in step 3, we're going to fill in all of the known information into the following table. Now, we will scroll back up to the picture to revisit the given information, but let's take a look at this table. There's a few things that are important to highlight. We can see that we have 6 values listed down the left-hand column here. And importantly, some of these values will be known no matter what type of projectile motion question it is. So for example, the initial velocity in the horizontal direction will always be the initial velocity multiplied by the cosine of the launch angle. We'll go back and look at the picture to see what that was in a moment. Similarly, the initial velocity in the vertical direction will always be the initial velocity multiplied by the sine of the launch angle. Now for the horizontal direction, the acceleration is going to be 0, and what that means is that the final velocity in the horizontal direction will be the same as its initial, so it will still be the initial velocity multiplied by the cosine of the given launch angle. On the other hand, in the vertical direction, under the influence of gravity, the acceleration will always be negative 9.8 meters per second squared. I often get the question whether it should be positive versus negative 9.8. It should be negative 9.8 because gravity is accelerating the projectile downward. So this is what we should fill into our table at all times for all projectile motion questions, so it's important to keep that in mind. Furthermore, for the time, we should know that whatever time we put into the horizontal direction, it will be the same as the time we'll use for the vertical direction. So these times will always be the same. Let's go back to the picture and begin to fill in the known information. Let's start with the initial coordinates for both the horizontal and the vertical direction. So you go back up and you look at your picture, and your initial launch point was over here. Sometimes it's helpful to even label that as initial. And hopefully we can see from our superimposed XY coordinate system that the initial coordinates are both 0. So the initial X coordinate is 0 and the initial Y coordinate is 0. And we would go ahead and fill that into our table like so. And then we look for the final coordinates. And we can tell from part A, since the question is asking us for the height lowercase h, that our final location or our final position will be over here. Now, of course, we don't know those coordinates. That's part of what we're looking for in part A. So for now, those are going to have to be left as an unknown. You might note in this case that the vertical coordinate at point A would be the lowercase h. If that helps, you can put that into the table. So for the vertical coordinate, we're going to say lowercase h. For the horizontal, we don't know that, so we will just leave that as x. And now we get to the velocities. We go back to the picture. We can see that it was launched with a speed of 42 meters per second, and then the launch angle was 60 degrees as given. So we will plug in 42 for v and 60 degrees, for theta. So here we would have 42 cosine of 60. Here we would also have 42 cosine of 60. And then over here, we're going to have 42 sine of 60. Why don't we pick up our calculators and punch those in to get them into simplified form. Make sure your calculator is set to degree mode. So 42 times the cosine of 60 gives me 21. So we'll actually just come over here and fill this in as 21. This is meters per second. The same will be true here for the final velocity in the horizontal direction. And then over here, 42 times the sine of 60 is 36.4 approximately. So we'll put that in for the initial vertical velocity. We do not know the final velocity in the vertical direction, so we'll just sort of keep that as an unknown for now. The accelerations are given, as we noted, they're always those values. And then the time, let's see if they gave us the time it took. They actually did. They said 5.5 seconds it's going to strike at point A. So we'll put 5.5 seconds into our table. And remember, if you put 5.5 seconds for the horizontal, you'll put 5.5 seconds in for the vertical. So that would complete the third step of any projectile motion question, is filling in the known values into this table. We will move now on to step number 4. Now in step 4, what we'll do is we will use a standard set of equations to solve for unknowns in both the horizontal and vertical directions independently of one another. It's important to understand in any projectile motion question, we can treat the horizontal and the vertical directions as independent of one another. So we will apply these equations twice, essentially. Once for the horizontal and then once again for the vertical. It is also important to note that we should be using a standard set of equations. Over the years, I've noticed students have all kinds of equations that they will use for their projectile motion questions. They vary from one textbook to another or from one professor to another. Get rid of all that and just use these equations right here. These will be the only equations you will ever need for projectile motion questions. So we're going to apply one or more of these equations, and we can begin with the horizontal direction. And we've filled in all of the information here. And in this particular case, if we look carefully, we can see that we know almost everything for the horizontal direction. We have the initial coordinate in the horizontal direction, we have the initial and final velocities, the acceleration, and the time. The only thing we're missing, which may become useful to us, is the final x coordinate. So in this case, because we know everything but one quantity, there's a number of equations we could choose to use. But let's just find one that has x conveniently situated in the equations. So we look around, and I've listed the equations in importance in terms of their frequency. So you'll probably end up using these three the most, and then followed by the last two. And again, we're looking for x right now. So it's probably best just to simply use this equation right here. And this will help us solve for x. Now remember, we're doing this in the horizontal direction, so we would write down the equation and begin to fill in our known values. Recall that the initial x coordinate was 0, so we would fill that in. The initial velocity for the x direction, or the horizontal direction, you can go back to the table if you need to, and the initial velocity was 21 meters per second. So you would fill that in for that v0. That would be 21 meters per second, multiplied by the time. That was given as the 5.5 seconds, so we'll fill that in. And then we have plus 1/2 multiplied by the acceleration. The acceleration in the horizontal direction is 0 meters per second squared, and then multiplied by the time squared. So that's 5.5 seconds squared. This is nice, of course, because this entire term here will just go to 0, and we would be left with x is equal to the 21 times 5.5. And when you work that out, you would get 115.5 meters. So this would be the final x coordinate for the horizontal direction. I like to go back and fill that into my table once I've figured out that information. So we now have everything we need to know in the horizontal direction. Now, to the vertical direction, we're missing quite a bit. We're missing both the final coordinate in the vertical direction as well as the final velocity. This particular question, if we go back, remember in part A of the question, we wanted the height lowercase h. So our goal right now is to find lowercase h. We don't necessarily care right now about the final velocity in the vertical direction. So when I go to look at my equations, I'm going to look for one that includes the final y coordinate, but I'm going to avoid an equation that possesses or that contains the final velocity because I don't have it and nor do I want it. So let's keep that in mind. Avoid the equation that has the final velocity in it. We don't need it right now. So let's just clean this up a little bit. And we look around, and in fact, this is the very same equation would be very useful to us right now. Now, please note that this equation is written in terms of x's. Right now, we're solving for information in the vertical direction, so we can rewrite this using y's rather than x's. So we would have y minus y naught is equal to the v naught times time plus 1/2 at squared. And we would just begin to fill in the known values. Now, we're looking for the final y coordinate, and we've symbolized that in this case by h, so we can put that in there. The initial y coordinate was 0. The initial velocity in the y direction, we just go back and look at our table, and it was that 36.4 meters per second. Multiplied by the time, which again was 5.5 seconds. We're going to have to slide this over. We're going to run out of room here. Plus 1/2 times the acceleration, which remember is negative 9.8. It's negative 9.8 times the time squared. We'll squeeze this in right here. Don't forget to square that time at the end when doing the computation. So here we go. We just punch this into our calculator, and this will give us the value for h. And it turns out to be about 52.0 meters. So this, in fact, would be the correct answer to part A of the question. And again, once you have that information, it is useful to go back to your table and fill it in. So this final y coordinate we could enter in as 52.0 meters. Now the only thing that we would be left with figuring out is the final velocity in the vertical direction. So we can just go back now and pretty much pick any equation that has the final velocity since we know everything else. So we'll clean up our workspace again, and we'll look for an equation that contains that final velocity. And I think the easiest one to use would be the first one. So we'll use this equation, and we'll just come over here, and we'll say that the final velocity is equal to the initial velocity. And again, that initial velocity was the 36.4 meters per second, plus the acceleration, which was the negative 9.8, and then times the time, which was 5.5 seconds. So we'll punch this in, and we end up with negative 17.5 meters per second as the final velocity in that vertical direction. So go back into your table and fill it in. So this is negative 17.5 meters per second. And so that is the basic rhythm of how to approach a projectile motion question. And there's some details here that we could investigate perhaps briefly. Part B wanted the speed of the stone just before impact at point A. So over here they want the speed at point A. I suppose we'll solve that before moving on to the next example. We don't need all the details right now. But for the speed at point A, we would be looking at the final velocity row right here. So all this information right here. Now we do have to be careful here because we have two different values. We have the 21 for the horizontal and then the negative 17.5 for the vertical. What you want to do is you want to draw a picture. Now the horizontal is positive 21, so you would draw a vector pointing to the right. Notice it's pointing to the right because it's positive and it's horizontal. So we would have the 21 meters per second that way. And then for the vertical, it's negative 17.5. Now, because it's negative, we would point that velocity vector downward and label that 17.5 meters per second. Therefore, to get the overall speed, you would be looking for this resultant vector right here. We could label that v. Hopefully, we can see that we have a right triangle and that we could use Pythagorean theorem to get that. So we would have v squared is equal to the 21 meters per second squared plus the 17.5 meters per second squared. We would punch in the right-hand side into our calculators. We would get about 747 for v squared. And then to solve for v, you would just take the square root on both sides. So take the square root of that, and you get about 27.3. That would be the final speed for part B. Now, I realize there was another part to the question, but what I want to do instead is just repeat this process, but with a more challenging example. So now we have a launch that is taking place above ground level, and we have a basketball player throwing a ball at a 55-degree angle, and then they give us a bunch of distances here. So we have the D1, which is this little gap between his toe and the release point of the ball. We have D2, which is the distance from his toe to the net, and then we have these heights, the height from which the projectile was launched, and then the height where the projectile lands. So there's a lot of different complicated labels here, but we can still follow the same process. So step 1 would be to draw a picture. That's been done for us already. Step 2 is to superimpose a XY coordinate system. So we have gone ahead and superimposed the coordinate system in this manner. There's a number of ways this could be done, so there is some flexibility to this, but what we've chosen to do is to put at the ground level and right where this D2 initially is marked as our origin. So that point right there in black, that's going to be the 0, 0 point. Now, from that origin, we would want to figure out the initial coordinates of the ball here, and then the final coordinates of the ball here, which we can actually do based on the given information. Let's just first label that point final, and then this point right in there, the initial. So to get the initial coordinates, we're going to have to know what this little gap here is, this little D1 distance. That's given as 1 foot. So the initial x coordinate of the ball's release point would be 1 foot. So we'll say 1 comma. And then the initial vertical component is whatever the height h1 is, and that's given as 7 feet. So 1 comma 7 would be your initial coordinate. We'll fill that info into the table shortly. And then the final coordinate would simply be the distance d2, which was given as 14 feet. So that would be your final horizontal coordinate. And then the final vertical coordinate would be the h2, and that's given as 10 feet. So it's really important to establish a good coordinate system, and that way you can label the initial coordinates and then the final if that information is given to you. Let's go ahead and turn to step 3, which is to fill in the known information. So here is that table that you should always use for any projectile motion question. We begin with the initial coordinates, and you will recall that we entered those in as 1 comma 7. So this would be 1 feet or 1 foot, and this would be 7 feet. We would have to convert these to meters later on in the problem. For the final coordinate, you would have 14 and 10. So 14 feet and 10 feet. Now, for the initial velocity, the question does not give us the initial launch speed or the initial launch velocity. That's what we're looking for. It does give us the angle of 55 degrees. So the best we can do is to enter this in as V0 cosine of 55. The final velocity in the horizontal direction would be the same. And then the initial for the vertical would be V0 sine of 55. That's the best we can do. We don't know the final in the vertical. We do know the accelerations, as always, and then the times were also unknown to us. So the fourth step would be to use the equations to solve for the unknowns. So here, once again, are those equations. We're going to be focusing our attention again on this second equation. We'll do the horizontal direction first. We'll use the information that we had plugged in. Now, recall that the final and initial horizontal coordinates were 14 and 1 feet respectively. So we'll have 14 feet minus 1 feet is equal to, the initial velocity was the V0 cosine of 55 degrees multiplied by the time t plus 1/2 times the acceleration in the horizontal is 0 times the time squared. This term will drop out, and then we'll just have 13 feet is equal to V0 cosine of 55 degrees times time. So we have two unknowns in this equation. Let's do the same equation, but we'll apply it to the vertical direction. So we'll need the final and initial coordinates in the vertical direction, which were 10 and 7 feet respectively. So we'll fill those in. And then the initial velocity would be the V0 times the sine of 55 degrees times time plus 1/2. Now, a little note here for the acceleration. Ordinarily, we would use negative 9.8 as we put into the table. In this case, I've decided to leave everything in feet, so the value for acceleration would not be negative 9.8, but would rather be negative 32, and that would be in feet per second squared. So that's just a little side note. That's simply because everything is given in terms of feet. So it's just more convenient to use that value for the acceleration. And then again, we'll multiply this by time squared. So this can simplify just a tad. We have 3 is equal to this V0 sine of 55 degrees times time. This will become minus 16t squared. So this is a more challenging example. The only way that we can really effectively solve for the initial launch speed, which is v0, is to solve this equation over here for the v0. So if you divide, to solve it for the time. Solve it for the time. So you'll divide both sides of the equation by the v0 cosine of 55 degrees. And that will cancel it out on the right-hand side. So then we see that time can be inputted as 13 over v0 cosine of 55 degrees. We're going to take this value for time and we're going to plug it in here for t and then also here for t. So we've made that substitution. If we look carefully here, the v0s cancel out right here. And then if we look really carefully, we have sine 55 over cosine 55. We know from trig that that would be tangent of 55. So really this first term on the right side will become 13 tangent of 55, and then over here we have the minus 16 times this 13 over v0 cos 55 squared. So the algebra here does get a little bit thorny. We're going to try to solve for the v0, of course. We'll go through that quickly just because this video is more about the setups than the calculations, but we'll subtract the 13 tan 55 from both sides. So if you do 3 minus 13 tan 55, the left side becomes about negative 15.6. And then we have equals that negative 16, and then that term in parentheses squared. Then I would divide both sides by negative 16. So now I have 0.97 is equal to that term in parentheses squared. And then let's take the square root on both sides. So if you square root the 0.97, you're going to get about 0.986. If you square root the right side, that cancels out the squaring. So you'd be left with this. And then we can cross multiply, perhaps. We'll multiply this way. So 0.986 times the cosine of 55. That's going to give us about 0.566 v0 equals 13. And then finally divide both sides by the 0.566, and you're going to get about 23. And since we left everything in terms of feet, this would come out to 23 feet per second. So that's the basic way to solve any projectile motion question. You just follow those 4 steps, and you should be very successful.